So let's take a look at some functions we should be able to differentiate or get the derivative of using our basic differentiation rules. We can get the derivative of f of x here using our constant multiplier rule and our power rule. So to get f prime of x, I'll bring my constant multiplier along 6 times, and then the derivative of x to the 5, well, the derivative of x to the 5 is 5x to the 4. I'm going to say that this is 30x to the 4. Now, in all honesty, when I think of the derivative of 6x to the 5, I don't even really think about that constant multiplier rule very much. I bring the 5 in front, and I multiply the 5 times the 6 that's already there. That's where I get that 30 from. And then I subtract 1 from the power and get the x to the 4th. So let's differentiate number 2. You can see we're going to use our sum and difference rule a whole bunch of times, and we're going to use our power rule a bunch of times as well. The derivative of 5x to the 4, if I bring the 4 in front, 4 times 5 is 20, and then x to the, I'll subtract 1 from the exponent. This will become 3. And then I'll subtract the derivative of 3x to the 3rd. If I bring this 3 in the front, 3 times 3 is 9. X to the, I'll subtract 1 from that. This will be 9x squared. Then I'll put my addition. Let me differentiate the 7x squared. When I bring the 2 in front, 2 times 7 is 14, and that's going to become x to the 1, so I'll just write x. Then I'll put my subtraction. Now I can approach the derivative of 4x using the power rule if I put my 1 there. When I bring the 1 in front, 1 times 4 is 4, but then this is going to become x to the 0, and we saw earlier that x to the 0 equals 1. 4 times 1 is just 4. The derivative of this negative 4x piece is just negative 4. And we know the derivative of a constant number, the derivative of 2, is 0. So there we go. We have our y prime. We know how to get the derivative of a whole bunch of pieces added and subtracted together, but we have not yet learned how to get the derivative of something divided by something. It's not as simple as just getting the derivative of the top and the derivative of the bottom. If we approached it that way, the derivative of the top is 0, and the derivative of the bottom will be 1, and 0 divided by 1 is 0. Well, I'm going to show you right now, the derivative of this is not 0. What I'm going to do first is rewrite f of x. I'm going to think of 2 over x as 2 over 1 times 1 over x. That's the same as 2 over x. And I'm going to think of this as 2 times x to the negative 1. Let me rewrite this as 2 times x to the negative 1. Now I have it written in a fashion that we can use the power rule. To get the derivative of 2x to the negative 1, I'll move the negative 1 in the front. So negative 1 times 2 is, of course, negative 2, x to the, and then I'll subtract 1 from the exponent. Negative 1 minus 1 is negative 2. And I'm going to rewrite this because I don't like to leave it with a negative exponent. This is negative 2 times 1 over x squared. And of course, negative 2 times 1 over x squared is negative 2 over x squared. I'm going to say our f prime of x is negative 2 over x squared. Here, once again, in number 4, we have a situation where our function is something divided by something. And it's not just as simple as getting the derivative of the top and putting it over the derivative of the bottom. If that were the case, this would be 8x over 0, and anything over 0 is undefined. Well, let me show you the derivative of this is not undefined. Let me rewrite this first. Let's think of 4x squared over 5 as 4/5 times x squared over 1. And of course, 4/5 times x squared over 1 is just 4/5 x squared. And once again, now we have it written in a way where we can use our power rule. So let's go get the derivative of y. We can calculate the dy dx, or change in y over change in x, by using the power rule. Let me bring the 2 and move it into the front, and 2 times 4/5 is 8/5, and then I'll put the x, and then I'll just subtract 1 from the exponent. And if I subtract 1 from 2, I get 1, so the derivative is 8/5 x. Here we have a function with a radical, but we should be able to use the power rule if we just rewrite the square root of t as t to the 1/2. Now you see we have a coefficient, a variable, and an exponent, so we can use the power rule. I'm going to say that f prime of t equals, and I'll take the 1/2, I'll move it in the front, 1/2 times 2 is 1, so I'm just going to put t, and I'm going to subtract 1. And if I subtract 1 from 1/2, I get negative 1/2. We don't want to leave it with that negative exponent, so we better rewrite it. This is 1 over t to the 1/2, or I'm going to say 1 over the square root of t. Let's try to make sense of number 6 here. Y equals 1 over 2 times the cube root of x squared. Well, perhaps you remember that cube root means a power of 1/3. So perhaps I'll rewrite this piece right here. The cube root of x squared, I'm going to write that as x squared raised to the power of 1/3. And I know when I have a power to a power, all I need to do is multiply these powers. Let me rewrite this as x to the 2/3. All right, I'm still not ready to get the derivative because I don't know yet how to get the derivative of something divided by something. I'm going to have to rewrite this. Let's think of this as 1/2 times 1 over x to the 2/3. And of course, 1 over x to the 2/3 is x to the negative 2/3. So this is going to be something we do often when we're using our basic differentiation rules. Take a function and try to write it with a coefficient, a variable, and an exponent. And now we can use our power rule. Now I can say that y prime equals, and I'll take my negative 2/3, I'll move it in the front, and negative 2/3 times 1/2. Negative 2/3 times 1/2 is negative 2 over 6. And of course, negative 2 over 6 reduces to negative 1/3. Then I'll put my x, and now I need to determine my new exponent. I need to take my negative 2/3 and subtract 1. Negative 2/3 subtract 1. I think rather than using the McFarland rule, I think I'll just get a common denominator. 1 over 1 is the same as 3 over 3. And of course, negative 2/3 minus 3/3 is negative 5/3. But you know we can't leave that negative exponent, so let's rewrite this. This is going to be negative 1/3 times 1 over x to the 5/3. I'll say the derivative is negative 1 over 3x to the 5/3. In number 7, g of x is written in polynomial form, so this one should be pretty straightforward. G prime of x, let's use our power rule. When I take the 4 and move it in the front, 4 times negative 1/2 is negative 2, x to the, I'll subtract 1 for 3, plus 3 times 3 is 9, x to the power of 2 when I subtract 1. The derivative of negative 2x is just negative 2, and the derivative of any number is, of course, 0. Number 8 appears pretty straightforward as well. The derivative of x is 1, and the derivative of sine of x is cosine of x. So I'm going to say y prime equals 1 plus cosine x. We've yet to learn how to get the derivative of something divided by something, so we're going to need to rewrite this one first. I can think of this as 1/2 times sine x over 1, and then I can rewrite that as 1/2 sine x. Now getting the derivative of f of x should be easy. F prime of x equals, I have a constant multiplier, I'll bring the 1/2 along, and then the derivative of sine x, recall, is cosine x. My derivative of f of x is 1/2 cosine x. Let's look at one last example. Let's get the derivative of y. The dy dx, or change in y over change in x of this function. Well, the derivative of 3x squared is 6x. The derivative of negative 5x is negative 5. And then I have minus, so I'll put minus. I have 2, which is a constant multiplier. And the derivative of cosine of x is negative sine of x. Well, of course, negative 2 times negative sine of x is positive 2 sine x. So there you have your basic differentiation rules. Now I think it's time for you to go try some.